Welcome everyone to our last plant breeding and genetic circle of the semester. Dr. Rutkoski is here to speak to us, and I'll turn it over to Shakira here in a moment to introduce her. But I did want to let everyone know that she has agreed to stick around for an hour afterwards to meet with anyone who would like to meet with her. There was some miscommunication with the email I typically send out, and it did not get forwarded on to everyone, I don't believe. But there will be a session directly after this that's open for all graduate students who want to join at the same link and have a more informal discussion. And there will also be one from 1:30 to 2 for anyone who would like to join in on that and have a conversation with Dr. Rutkoski after this. So with that, I will turn it over to Shakira.
Howdy all, I'm Shakira Nakasaga, working with Dr. Seth Murray at the Corn Breeding Lab. I'm introducing Dr. Jessica Rutkoski, who is an assistant professor in small grains breeding in Illinois. Particularly, she is working on winter wheat. She received her bachelor's degree of science in genetics from the University of Wisconsin in Madison in 2009. And she received her PhD in 2014 from Cornell University, where she stayed and worked as an assistant professor in collaboration with CIMMYT in the Global Wheat Breeding Program. And in 2016, she also worked at the International Rice Research Institute in Philippines to improve rice breeding efficiency. That's a short introduction about Dr. Rutkoski.
All right, great. Can everybody hear me just fine?
Yes, sounds
Okay.
good.
Good. So yeah, today I'm going to be talking about my work here at the University of Illinois, and where I work on primarily winter wheat and breeding more profitable wheat varieties for Illinois and beyond. I'm a plant breeder, and I'm a firm believer that plant breeding is actually a dynamic science. As plant breeders, we're constantly innovating, coming up with new ways of doing things and borrowing ideas from other disciplines and doing things just to make plant breeding more efficient. And it's this progress that really keeps us moving forward. Just to highlight a few of these kind of interesting innovations over the years, things like off-season nurseries, single seed descent, and selection indices. These were actually new back in the 50s and 60s. And then, 70s, 80s, and 90s, we saw the influence of marker-assisted selection, computer simulation, and statistical techniques, and other molecular tools. And then 2000s onward, we've all witnessed the influence of bioinformatics and the development of methods like genomic selection and high throughput phenotyping. And so it's this constant change that really makes plant breeding an exciting field to work in. And it's absolutely been really, really exciting to be a plant breeder. And it's as a result of innovations like these, as well as agronomic advancements, and thanks to our stakeholders, agricultural productivity has been improving at an impressive rate. So here is just showing US agricultural output over time, and it's at this steady increase, and it's this progress that I think wouldn't be possible without innovation and just hard work and incremental progress. However, serious challenges remain. We have issues with profitability. So here in the state of Illinois, average net income per farm has been cut in half in recent years, which is a real challenge that we have to think about. At the same time, we have environmental concerns. So in the state of Illinois, especially, we are one of the biggest contributors to nutrient runoff going into the Gulf of Mexico and creating a dead zone. And this, of course, has a wide range of unfavorable consequences. And so it's really not just that we have to focus on improving productivity. We have to think about the whole picture, the profitability and the environment. And cropping system diversity can help address these challenges. And here in the state of Illinois and surrounding states, we're in the Corn Belt, and the short, corn soybean rotation or continuous corn is really common. And small grains could be a very useful addition to the cropping system. And to some extent, people are incorporating small grains, especially wheat in the region. And there was an interesting study by actually the head of our department, Dr. Adam Davis, and he did a study to compare rotations that included small grains and also a short corn soybean rotation. And he found that there could be equal profitability with either, but the rotations including small grains had greater profit stability. And there were some environmental benefits like less freshwater toxicity, less agrochemical use, and there was actually equally effective weed control in spite of these reduced externalities on the environment. Winter wheat is the most prevalent small grain in Illinois, and although it's not really a major crop, it is really important, and it is a really important part of the cropping system in the southern part of the state. In southern Illinois, most of the wheat is grown as part of a double cropping system with soybean. So the wheat is planted in the fall, it goes dormant in the winter, and then it's harvested about end of June, and then soybean is planted as soon as the wheat is harvested. That system is actually turns out to be more profitable, especially in recent years in Southern Illinois, than other crops. So this graph shows on this blue trend line, the profit from the double crop soybean. So that's the combination of the wheat and soybean compared to the profitability of other crops, just like soybean alone, corn alone, and wheat alone. And I believe that if we can focus on improving the profitability of this system in our region, wheat could become an even more prevalent part of the cropping system to help diversify the agricultural landscape, and while also benefiting growers' overall income. And in fact, this is one of my major aims of my research as one of the project leaders in the Illinois Small Grains Program. A little bit about the program. We are a combination of 2 research labs working on small grains breeding. The majority of our research is really geared towards the field and conducted in the field. And so we have one combined large-scale field program, but we have a winter wheat breeding program as well as an oat breeding program. And we use our applied breeding experiments also to conduct research on breeding methods and ways to accelerate the breeding cycle that we hope can impact not only our breeding programs, but other breeding programs of other small grain programs or even other crops. We have a vibrant and high performing team, and we really, really enjoy what we do. So the PIs include myself and Dr. Juan Arvilaiz, and we have several student interns working with us at a given time. We have research specialists. We have teamed up with the variety testing program. And so we're coordinating on a lot of our field work. And we have postdocs, we have a visiting scholar, a couple of grad students. And I think together, last time I checked, we were 15 people from 7 different countries. And everybody, we all work together as a team. We're all passionate about plant breeding. And so it's this environment that makes it really exciting and fun to come to work every day. And it's also thanks to this excellent team that I've been able to develop and start implementing a new winter wheat breeding strategy. When I came, I inherited a program, and in the beginning I thought I'll just slowly evolve over time and make it, make small changes here and there. But then at one point I came to the realization that it will be just much easier to completely change, to start from a blank sheet of paper and say, how do I want this program to actually look? And then what do I need to do to get to that point, to transition to that? And so that's what I did. I decided to completely change the strategy and design it to maximize the rate of gain. There are basically three components. The first one is on developing the lines. So I use speed breeding, getting lines as quick as possible using greenhouse generations, and just getting to a fixed line and not really concerning myself with selection during that process. And then once the line's developed, genotype those lines, do genomic selection, and decide what parents to cross. Then also when those lines are developed and at the same time that they're being genotyped, I'm also testing them in multiple locations. And my philosophy has been to try to get to a multi-location test as soon as possible. And to do that with limited seed amounts, I'm using a sparse testing strategy. And I do things a little bit differently in that I also fully randomize across all breeding stages, so that it simplifies a lot of factors in the field. It also simplifies analysis and makes it better for training the model for genomic selection. All these decisions that I made on how to set up the program, it's really been all based on looking at, in a quantitative genetic framework. So looking at the breeder's equation and determining what are the points, what are the variables where I can have the most impact with a fixed budget. And the two that are really key for me, thinking about how to work with a fixed budget and maximize my resource use efficiency, it's been accuracy and time. And so getting to that multi-location yield test and using marker data to gain accuracy as I'm doing selection, that's been a big change that will help improve the rate of gain. And then the time, by moving things ahead in the greenhouse faster and by using genomic selection to select parents, that will drastically reduce the time and allow me to get more cycles of selection in a given unit of time, thereby increasing my rate of gain. Now that's the strategy. Now what about the objectives? Obviously, without clear objectives and without really having the right objectives, no amount of genetic gain is going to get you anywhere. And so because I'm focused on improving the profitability, what better way than to select for profitability itself? And that's exactly what I'm doing. I use data on individual traits and combine it using a profit function. And then I select based on profitability itself. So I take yield, maturity, vomitoxin, also called DON, D-O-N, and test weights. Those are the four main traits that affect the profitability. And I have determined how to put all those variables into a formula that tells me what's the profitability of a line. So at the end, I just get one number that is really what I'm basing my selection on. Now I want to get a little bit more into the nuts and bolts of a couple things that I'm doing that I think are really interesting. One of these is this cross prioritization app. So what I do is I take the profit function and the data on individual traits, and I get a net merit, so the expected profitability of every line. And not only do I get that for every line, but I get that for every combination, for every cross combination. And then I have a ranking. So I determine what's the top ranking crosses in terms of profitability. And then, as I was actually doing the crosses and getting the crossing block ready and all that, I realized that it's actually not, when you're making crosses in the greenhouse, actually not that simple and easy to show up and say, okay, what's the best cross to make that day? That's actually kind of time consuming to go and figure out, okay, what can I make today? Then check your list. And I said, I could make this a lot simpler. So I developed an algorithm that you input what's available that day, what crosses can be made that day. And then there's an algorithm in the back that will tell you what are the combinations, the best ranking combinations in terms of profitability that could be made that day. And then it's very simple. You have a list, what parents are available, then you put that in, and the output is the combinations, the best combinations you can make that day. And then you have your team in the greenhouse and you divide them up. It's okay, you take these crosses, you take those crosses, and then it just takes all the guesswork out of it. And at the end, when everything is ready, I end up having the best possible crosses that I could have made. And that's been really fun to work with. And I hope in the future I can make this a nice product that other people could possibly use and continue developing on. Now that's the crosses. And as I said, my philosophy is to get to a fixed line as quick as possible, not doing too many selection steps or any really in between. I get to a fixed line and then I go straight for yield evaluation and testing it in multiple environments. I have 4 locations. There are at least 6,000 yield plots, and outside of the state of Illinois, I also have 4 locations where I test a limited, like a very small set of lines for the purposes of variety release. And that yield evaluation, it's a really important and huge component of the program. As I was mentioning, I do things a little bit differently with my field design. I take all the yield trials at any stage, regardless of breeding stage, and I put them together in one yield trial. And I use blocking to control the error. I use partial replication, and I take advantage of the fact that the lines at later stages of testing can be replicated because we have more seed of them. And then the lines at earlier stages of testing are the unreplicated ones, which we don't have very much seed of. So it kind of works out perfectly where I'm able to really utilize the space very effectively by using my replicated entries at advanced stages as the checks. And then every field has just one randomization. So that really cuts down on the amount of confounding factors. And I don't want to have my experiment trial effect confounded with any genetic effects. And so that's what that accomplishes. Here's just an example of a single field in Urbana 2021 where I've done this. And here in green, I'm showing you those are the unreplicated entries. Those are the earlier stage of testing, I should say. Not they're fixed lines, but they're at an early stage of testing. And then the shown in white are the plots that are the replicated entries, which are at the advanced stage of testing. This is really, this is nothing new. This is just a partially replicated design. What's new is that I think this is really underutilized, and so it's new because we're probably it's probably one of the few people, at least in my circle, that is actually doing this. And then for the multi-location testing design, I take it a step further, but it's really the same philosophy with partial replication. I have different breeding stages. So say, for instance, breeding stage 2, 3, and 4. And then I have 4 locations. And I take a quarter of the lines in breeding stage 2, a random 25%, and they go to one location, location 4 here. Then I take, again, 25% of the lines in breeding stage 3, put those in location 4. I also take another 25%. So now in total, I actually have half of breeding stage, the next breeding stage in my location. And then the last breeding stage, I put all of them replicated. So I have replication within a location, and I also have connection between the locations. Now that was the yield evaluation. The other really important trait that affects profitability is scab resistance, because vomitoxin, or DON, deoxynivalenol, is a toxin that the pathogen that causes this disease causes in the grain, and that really reduces the price of the grain at the grain elevator. So scab resistance is a really big trait, really important, and we put a lot of effort into evaluating resistance to this disease. We have thousands of small plots each year in a misted and inoculated nursery. This is something really haven't changed. I think the system was pretty well done and very effective. For the evaluation of scab resistance, it's a really tricky trait to evaluate and also improve. So it's a quantitative trait. It interacts with the environment. Its heritability is moderate. There are multiple phenotypes that typically get measured, like incidence, severity, kernel damage. And then finally, the trait which is most important, DON, or vomitoxin, is evaluated once we harvest the grain, we grind it, send it to a lab, get the data back. Unfortunately, the DON data is not available in time for selection, for us to make the selection decisions. And so that is a kind of a problem, because it's really the most important trait, but we don't have it available in time for selection. We have all these other traits available. With that in mind, one way to overcome these challenges is to actually implement multi-trait genomic selection. It seems kind of like the perfect scenario in which this method will be useful, because what we have a primary trait, which is the vomitoxin, the DON, and then we have secondary traits like the incidence, the severity, the kernel damage, and we have our marker data because we're genotyping everything. And we have all that data from the previous years. We have all that complete data set. And then we have our new breeding candidates where the DON data is not present. We don't have it yet because it's still being evaluated in a lab. And then we have our phenotypes from the secondary traits, the traits other than DON, like the incidence, severity, kernel damage, and we have the marker data. And so what we can do is actually fit all this data into a model so that we have our complete data on the training set. And then in our new breeding candidates, we have all this data except DON. And we can put all that into a multi-trait genomic selection model and get really accurate predictions of breeding value for DON, which is our trait that has very high economic value. We tested this in a couple of different breeding data sets, one from the University of Illinois and one from Purdue. One of the questions that we wanted to answer was, do we really need to be phenotyping all of those secondary traits? Is it really necessary to go in and evaluate severity, incidence, and kernel damage? Because it really does take, it's very time consuming. We actually have to hire quite few people just to make sure that we get all that data on all those plots. And so we evaluated what would happen if we have different traits in the model. Here on the all the way to the left, the box plots show what if we don't have any secondary trait data. So just it's a simple univariate genomic selection model. And then the other boxes to the right show different combinations of traits. The first one to the right is FDK, fusarium damaged kernels with DON. And then the other ones, the next one over is stage 2 heading, fusarium damaged kernels and DON. The next one is incidence, severity, and DON, and so on. And what we see is that all we really need to include is fusarium damaged kernels. If we add other traits beyond kernel damage, we don't see an improvement in accuracy. If we remove FDK from the model, then our accuracy takes a big hit. So what that tells me is that all that effort that we're spending to evaluate these secondary traits, really, we have to think very hard about that and whether or not we really need to be doing that in the future. And thinking about this even further, there are even some research going on. Okay, can we evaluate incidence and severity from a drone? And think about it. Maybe we don't need to do any of that. Maybe that it will just be excess information. And so I feel like we really have to think hard about how do we kind of work with all these competing technologies, and they're kind of like the multi-trait genomic selection is kind of disruptive of high throughput phenotyping and vice versa. And so we always have to question what we're doing, kind of take a step back. And I think this example shows that sometimes the conventional wisdom of take as much data as possible may not really be applicable in every situation. Now, given that FDK is such an important trait, we really focused in on how do we make that phenotyping more accurate and also quicker and easier, something that will require less skill and training to do. And one of the things we're working on is developing like a deep learning approach to take this data rapidly and with really no training. So we took image data, and I'm collaborating with another professor who specializes in this area. And we're, we've tagged all these images with diseased, healthy, or normal kernels. And the idea is to try to develop a model that will allow us to actually phenotype FDK from an image. And the dream is that we will develop a simple device where we can dump the grain in and get an FDK evaluation quick and with really no training. Now I'm getting towards the end of the talk, and I want to actually kind of take a step back and acknowledge all the wheat breeders in my region and my predecessors who have made it possible for me to be able to actually do all this exciting research and work, and that has given me the kind of all this wonderful germplasm that to work with. And I always like to say I stand on the shoulders of giants. I wouldn't be able to do any of this work without what they have done and their hard work over the years. And this slide actually just shows the progress from 20 years of scab resistance breeding in the eastern soft wheat region. So all my colleagues and predecessors, their efforts in breeding scab resistance and what genetic trends have resulted from that effort. And what we see is that we see very strong signal, a strong and robust trend down, reducing the fusarium damaged kernels and deoxynivalenol. And so huge progress has been made. And this is really important because I don't want I don't want to make it sound like the past is bad and new ways are better, and everything that was done has no merit, because that's definitely not true. I mean, there's been huge progress from all the existing, breeding methods and all the hard work that has gone into it, and the expertise of all these breeders, and that definitely needs to be acknowledged. And I think that these ideas can coexist. We can acknowledge that the past was very effective, and amazing work and outputs have been done. At the same time, we can continue to move things forward and continue to innovate and improve the process. That's the end of my presentation. I just want to acknowledge all the people that contributed to this work. They're all listed here on the slide, as well as all the funding sources that have contributed to my research. With that, I think there should be plenty of time for questions. And you can always also email me here, but I'll go ahead and take questions now.
Thank you, Dr. Rutkoski. Very interesting. It looks like we have a question in the chat. I don't know if you can see that, but what are the root or crown traits that would be valuable to phenotype?
Roots or crown traits? Well, I guess my question back to that question is, what's the economic value of that trait, or what trait of economic value would those traits be associated with? And I guess that's my main point is, my priority is to phenotype the traits that have economic value, or find traits that are very highly genetically correlated with those traits of economic value that could be used in multi-trait selection. So, I don't know what root or crown traits might be associated with my traits of economic value, but that's kind of how I prioritize what traits to phenotype.
So I have a question for you. I don't know a lot about the other traits of importance in wheat in Illinois, since I'm in Texas, obviously. But are there other resistance or things that you're looking at that would fall into that profitability area, or are you really focusing on that one resistance?
So I didn't mention that. Okay, there are these main traits that affect profitability. There are kind of other traits that don't really fit into the profit function, right? But they're kind of they're more like marketing traits. So there may be value added to them, but they don't really fit into that. So for instance, soil-borne mosaic virus resistance, it's not something that really factors in to the profit function at this point, but we phenotype it, we make that data available. If somebody is interested, if a farmer is interested in that, they will have that ability to make a decision and factor that in. But it definitely does leave a lot of traits that you think, well, okay, this doesn't, it's not really factoring into profitability. It's not really a priority for selection. And those are the kind of traits where I say we just need to maintain them. We need to maintain variation in the population, but I don't necessarily need to be pushing genetic gain for those traits. I didn't talk specifically very much about the other two very important ones, which are early maturity and test weight. But those factor into the profit function. in a very big way. And so those are, definitely what I spend a lot of time focusing on as well.
Catherine has her hand raised.
Yeah, thank you so much for your great presentation. I was wondering about your cross prioritization app, and I'm wondering if it's available for everyone to use, and also like what factors are considered in the software in order to prioritize the process for every day.
Yeah, so I'm definitely willing to share the code. It's not in a very fancy or it's not it's not really made for like mass consumption at this point, but I'm definitely willing to share it. And in the algorithm itself, what it looks at is for every, so you give it a list, what males and females are available, then it goes and says, what's the very best cross that can be made, and say, okay, based on the profit function. And then we'll say, okay, make that's the best one cross that can be made. And then you have to take into account that you're going to use those plants. So you have to delete then that male and that female, and then recalculate again, what's the next best cross that can be made, and then delete those plants from your list that are males, potential males and females, and it goes down the line. And there's also an option to make multiples. You can say, I want to make duplicates of the same cross. Also takes like, if the cross has already been made, like what's the maximum number of duplicates that you want to make of a certain cross. So that's basically all it really accounts for.
Sounds good. Thank you.
Yeah, you're welcome.
Jessica, you mentioned, and I appreciated the incremental and the financial based trait identification. But Dr. Borlaug frequently spoke of the transformational change, the traits that would disrupt the market and change the way wheat's valued or change the way a trait is valued. How do you, are you looking at any, what I will call disruptor traits? And do you keep a portion of your program for working on some disruptor kinds of technology? Right now, there's no market for really enhanced quality in wheat.
Right.
But if we could disrupt the market by truly having a breakthrough, and I think Dr. Borlaug described that by like a minimum of a 30% difference, but more likely a 50% difference. I've babbled enough. I'll leave it there.
I have some ideas, like, some of these kind of niche quality traits that, I just made a couple of crosses this time. And, at this point, I feel like it's, there isn't any one trait that I feel confident has that disruptive potential but I kind of do play around with that a little bit. So I don't know. I think if I see an opportunity, I will seize on it. At this point, I haven't thought of a trait that could be disruptive, that I really truly believe will be disruptive. Yeah.
They don't come along every week.
Yeah.
So in your introduction, you showed the nitrogen issues going through the waterways, and you didn't touch much on sustainable traits or ecosystem service traits, but it sounds like you're thinking about it. So how do you plan to address that, assuming you do in the future?
Well, I think the main way that I'm addressing it is just by trying to get wheat on more acres in the state. So I think that's, just in expanding. I mean, I've been told, or from what I've gathered from different presentations I've been to, is that if we can really put cover crops out on a large scale, we will address a big chunk of that problem. And so wheat acts as a cover crop as well as a cash crop. And if we can get that out on more acres, like we can kind of kill two birds with one stone and help improve profitability and reduce that runoff. My colleague Juan is focusing a lot on the cover crop, just making cover crop more viable. So making that, releasing varieties for oat and other crops for cover cropping. That's been my approach. I haven't really looked at like improving wheat specifically for that purpose. Yeah.
Hi, Jessica.
Mm-hmm. Hello.
Amir Ibrahim is here. Thank you for the seminar. Can you hear me well?
Yes.
Yes. So when you succeeded Fred Cobb in Illinois, you said you changed things a lot. I mean, I would say decided to have a new program, right? Well, don't you think that the risk reward ratio here is very high, that you can get a lot of great things, but by the same token that you are you don't have enough diversity in the breeding methods and approach and things like that? That's one question. The second question is, is your genome selection heavily focused on scab per se?
Mm-hmm.
And the last one is, to follow up on David's question about, disruptive traits.
Mm-hmm. Mm-hmm.
Wheat acreage is going down, and we're back to 1903 acreage a couple of years ago. And so new uses like nutrition, maybe bioavailability of zinc and iron, some quality and flavor traits, things like that. Do you think that this might be invested into?
Yeah, so I'll try to, you have to remind me the first question now.
The first question was the approach you've taken to change the style of Fred Cobb.
The new strategy of breeding.
Yes.
Yeah. Well, I don't have too many concerns about that. I should make it clear that all the germplasm I'm continuing it. There's continuity in the germplasm. So I'm not like starting from scratch with the breeding population. It's all the same germplasm. We're moving the same populations through. For the new crosses, I'm using these new approaches. I don't really have any concerns with that in terms of like, because I feel like it's pretty, the results are kind of predictable. I can predict what's going to happen with the strategy that I've developed. So, and then what's the second question? Oh, your mic is off.
Dr. Abraham, we can't hear you.
Because I was on mute. Sorry.
Oh, yes.
The second question was on your genome selection. It's heavily focused on scab.
Well, actually, it's focused on all the traits that I am selecting for. Yeah, okay. I just showed you the one results because I think it was an interesting set, use and situation where, we saw that difference in prioritizing, our phenotyping efforts. So, but it's, being used for yield and days to maturity and everything.
Okay.
Yeah.
And then the last one was on the disruptive traits.
Oh, yes. Yeah, the disruptive traits, it's something, like I said, I've made a few crosses with kind of weeds that I feel like I could probably develop a niche, a variety with, but at this time, my confidence in that actually being disruptive is very low. So I feel like I'm going to develop it and work on it, but it's a bit of I feel like that probably won't disrupt. It probably won't make like wheat is super profitable, just because if it was that easy, somebody would have done that already. So, but who knows? Maybe things will change. I don't know.
Okay. Well, thank you, Jessica.
Yeah, you're welcome.
So you mentioned on the environmental part, getting wheat on more acres as a cover crop. What are the barriers to that? Why is that not already happening?
I believe that it's the profitability that is the biggest barrier to that. Yeah. And if you look at one of the slides I showed, wheat actually alone, if it's not in double cropping, it has a negative profit. That means people growing wheat lose money to grow wheat. That's a big deterrent.
So you mentioned UAS or drones. Can you talk maybe a little bit more about how if you're going to implement them, how you're implementing them? Is it your program or working with colleagues?
Yeah, at this point, it's something at this point, I've just been collaborating with another group that takes the data, but that's something that for the next season, it's on my list of things to do. And I really want to, with the high throughput phenotyping, I really want to get more data from my multi-location trials, because that's something where we don't take, we're not taking any other agronomic data. And days to maturity is extremely important for us with trying to get earlier maturing, but also high yielding wheat that will go fit in the double cropping system. And that's going to be my primary
I found this on the web.
Target for what I want to get out of high throughput phenotyping. And then I have some other ideas on doing like I think this is not necessarily a new idea, but actually taking sparse testing to another level, to where we'll plant a much larger trial than we will and only harvest 50% of it, so that we're able to do more testing in multi-locations and then kind of impute the phenotype using the high throughput phenotypic data.
I think that's a great plan. How about are you planning on having people in your program do the work? Are you outsourcing that, or?
Yeah, so far, just with a couple of grad students and a research specialist, my plan is that we obviously take the drone data ourselves and possibly outsource the analysis of it.
So Jessica, you are mainly soft-red winter wheat, right? Do you have any work on hard?
No.
Okay.
Mm-hmm.
But do you see any potential in that in Illinois and surrounding states?
I don't think hard wheat. I think one of my cooperators is an organic farmer he's very he likes to take risks, and he's tried for a few years with hard wheat, and he actually decided that it's not worth it. Like, it's really doesn't do well, and which is surprising, and I sort of feel like if he's not going to do it, then nobody will, because he's a big risk taker. So that's an anecdote, and I don't have any better data than that, but I feel like doesn't have much potential here.
Yeah. Thank you.
You're welcome.
Do you do the quality in-house, or do you send things to Worcester, Ohio?
We send that to Worcester.
Okay.
This is your chance, students. We need to hear from you. Questions?
Jessica, great presentation. I just had a quick question. So what percentage of your program's budget goes to phenotyping compared to genotyping? And how do you envision that changing in the future?
Actually, that's a really good question. I'd have to think about that because right now my genotyping is paid for out of projects where I don't directly pay for it. It just comes out directly from, it's like, it comes via the project. So I would say probably 75% is on phenotyping, 25% genotyping. I hope genotyping will become cheaper. I don't, I don't see phenotyping getting that much cheaper. In fact, it may get more expensive because of, rising costs of labor and land and everything else. Maybe that will stay about that same, breakdown in the future. I'm hopeful that genotyping will become cheaper, but that doesn't seem to be happening as fast as we all thought it would.
So based on that, with the results you got showing that the extra phenotyping didn't really give you more accuracy, are you already prepared to cut a lot of that out, or are you still going to continue to keep it and we'll get more results?
I will get more results for another couple of years and really determine, because the thing with scab resistance, even though we did test in 2 different data sets and we had different environments, there could still be environments or over multiple years where it will end up providing some benefit. And the other reason I will keep doing it for a couple of years is there may be some benefit to developing. So there may be some benefit to using only those visual traits, because fusarium damaged kernels is very labor intensive. You have to measure, you have to harvest every single plot, thresh it, clean it. And so the result showing that that's the most important trait and that's, you don't need anything else, that really doesn't help much, because you're still putting, the majority of the effort is really spent on that trait anyways. And so I still have hope that maybe we can find something else or phenotype in a different way that will make FDK less important. So still something to evaluate, but yeah, unfortunately, I think we will be stuck with FDK phenotyping. But give it a couple of years and we'll see.
It's always the most time-consuming one that you have to keep, right?
The most important one is the hardest one. So that's the way it goes.
Thanks.
Jessica, can I ask another question?
Mm-hmm.
Okay, so in wheat, we rely on making incremental gains, via adding the additive effects. And since you work a lot with the scab, that becomes really difficult because you have to maintain resistance at the expense of yield and quality.
Mm-hmm.
Do you have any ideas about achieving some quantum leaps in yielding ability in the future? What are you doing towards that?
Yeah. I don't have a lot of faith in that, and I kind of that's maybe my philosophy. I believe that we can make incremental progress and it's predictable. We know we can do it. So I'd rather invest in that it's kind of like, would you rather put money in your 401k or would you rather buy lotto tickets? I mean, that's the way I see it. So I'd rather put money in my 401k than just go buy a lotto ticket every day. That's kind of my philosophy, I guess. And maybe it also has to do with my interest as a quantitative geneticist as well.
That makes sense. Thank you.
There's a question in the chat that says, since you have experience in both rice and wheat, do you see that genomic selection works equally well in both crops? And are there any changes needed for the different crops?
Well, definitely with rice, the genotyping is much more, you can get the data quicker. There's much more options for cheaper genotyping. And that's something I'm very envious of now that I'm in wheat again. So I really would like to have a low cost, rapid genotyping kind of setup or like service or something, which was something that rice has. And that's crucial for implementing genomic selection. I mean, other than that, I don't see that big of a difference in terms of like effectiveness. So.
And where you're genotyping, at what stage are you actually collecting tissue, and how fast do you get those results back?
Yeah, I'm genotyping at the F4 derived stage, and this year is not a good example because obviously we had the pandemic and that shut down labs, but I sampled the tissue in November and I'm getting the data back around now. I really hope that it will be in the future. What I would like to do is be sampling the tissue in May and be getting the data by at least September.
Yeah, I guess when I was asking about stage, I meant stage of the plant. So are you doing that?
Oh yeah, leaf tissue.
Shortly after you plant them, you going out in the field and collecting tissue, or?
So in the new system, I'm going to be vernalizing the plants in the indoors and then transplanting them, taking them out to the field, and then after transplanting, taking leaf tissue samples. So it's seedlings, but it will be done in the field. This past year was a little bit different. So switching, I'm still kind of halfway between the old system and the new system. And this year it was just, planted in a 96 flat and take leaf tissue samples. Yeah. Interestingly, the cost of tissue sampling is like $2. I calculate that it's actually $2 a sample. So I think that's very underappreciated, but there's a cost there that is something that's probably not going to be eliminated anytime soon.
Well, that's just the cost for DNA extraction. You got labor there too, right?
Oh no, but I mean just sampling the tissue costs $2 a sample. Then on top of that is DNA extraction. So,
And that $2 sampling cost, is that just for tubes, or is that including your labor?
That's labor. That's just labor.
Okay.
Yeah, Jessica, Amir again. Do you use the T3 database and Pollen's software, or do you use something more advanced like Agrobase or for database management?
I'm using the breed base.
Okay, the breed base, okay.
The next iteration of T3. Okay. And yeah, I'm totally on board with that. Like I put everything I transitioned from Agrobase to that system, and now I'm fully in that system. I generated all my trials there, field books there, all my historical data is there. So
that's great. Thank you.
You're welcome.
Any other last minute questions? Okay, thank you again for coming and speaking to us. If graduate students want to stick around here for the next 30 minutes to have more conversation with Dr. Rutkoski, please do so.
And Ellen, we're using the same link when we come back at 1:30?
Correct.
Okay.
So this is a 30-minute break, or I continue?
Continue.
Okay, continue.
That, unless you need to take a break.
No, I'm just making sure I understand, right? Yeah, okay.
And like I said, I don't know how many people will be able to stick around since the email didn't go out, but. So I have a question for you as a graduate student. I know this is kind of a really big question, but thinking about going on and starting my career after I graduate, the idea of stepping into a role and somebody handing me a breeding program and saying, there you go do, is really overwhelming. And obviously that may not happen right at the beginning of my career. Hopefully there will be some steps before that. But when you got into and were handed a program, you said you didn't start from scratch, but what were some of the steps you took to get going? Did you have mentors or other people that you reached out to get ideas? Did you already have ideas from previous experience of exactly what you wanted to do? How did you start that process?
Well, definitely because, you know, I had a lot of time between when I graduated and took this program. Basically, I already knew exactly what I wanted to do in a way. Like, I knew there was always, like, before when I was not leading a breeding program, I would always see, like, I wish I could do this. I wish I could do that. And so then when I came here, it was like, okay, now I can finally do it this way, the way that I've always wanted to do it. And so that kind of, yeah, it was like there was a lot of time for me to formulate those kind of ideas and ways I wanted to do things. Yeah, and I mean, yeah, and I think also what was really beneficial was like I kind of had different roles, like and I learned different components of like breeding tasks in different stages of my career, I guess. So I at Erie, I had a lot of experience with kind of designing the trials and getting all those kind of, you know, make custom designs and things like that. And then when I came here, I already knew exactly how I wanted to do things. And then previous to that, you know, I had been working with genomic selection and multi-trait models. And so I had that experience and I kind of learned all that. It's like the only thing that was kind of new for me in this position was like working, like actually like laying out the trials and like planting, like using driving the tractors and that sort of thing, and pouring packets. That was something I hadn't done before. And so that was something I learned here, which was awesome because like I always like to learn something new. So yeah, I think those sorts of things is probably the parts of the program that I have changed the least because I don't know that much about it. And so that's changing, but that's changing as I learn more. So yeah, I think it just depends. I think having that experience of like learning all the different components and then taking over a program, I think that definitely helps.
I had another question related to that and it just left my brain. Oh, so did you work with rice first or wheat first?
Wheat first.
So do you think running a program now, was it helpful to work with a different crop? Did you gain things from that you took back to the wheat program later?
Well, not necessarily. Like, I mean, the crop wise, I mean, I don't know if it mattered that much. Like there wasn't, yeah. I think just exposure to different programs is what really helped, because every program kind of has their thing, like the way that they like to do things, or they have different things that are like, yeah, just the way it's set up is different. And kind of seeing all of that, it kind of gives you perspective on like what is possible to change and modify, and what, you know, it's like, oh, because you've seen it done different ways, so you know that, okay, it gives you the confidence to say, I could do this differently. I know that their programs, they are really diverse in the way they do things. And yeah, I'm sure that there are things that I learned that I'm just not recalling at this moment, but that, you know, coming from rice breeding in particular, but I can't think of any off the top of my head right now.
One of the reasons I ask is I'm in wheat currently, and I'm looking into possibly doing an internship next year. And I was trying to think about, do I want to try to do something in wheat, or do I want to try to branch out and do something different to get that experience? So something I'm thinking about.
Yeah. I think branching out is very cool. I think it's great. I think it's like, if whatever you can learn the maximum is the best choice. That's my philosophy.
Leo, I don't know if you are where you can talk or ask questions, but I don't want to dominate the conversation. So if you have questions or comments, please jump in. So is there anything when you were in graduate school outside of the typical research and courses that you did or experience you had that you really felt prepared you for your career, or that you're really glad you did?
I mean, my research itself was something that really prepared me. Just having that experience of like, because in my PhD, I had a recurrent selection population. So I had all the steps, you know, I made the crosses, the population, designed the trials, you know, phenotype. So that experience, other than that, I mean, the classes, I mean, I think classes are important, but just like doing the self-study, like reading on my own, and I'll actually like contributing to courses and teaching was also something that really helped me a lot, because I think that I just feel like everybody has a different learning style, but for me, just reading and studying on my own, I had learned so much that way. And in addition to, well, our lab we had lab meetings, and I learned probably the most from those lab meetings, as well as self-study.
I do find that I teach as an instructor at a different university, not A&M, but I do find that when you teach something multiple times, it tends to stick. So teaching is definitely a good learning method.
Well, yeah, and it's like it's a good way to force you to learn something new if you have to, because it's a deadline. That's like, you have to do that lecture. So if you need to refresh it, you have to. There's no way out. You can't procrastinate. You can't. So yeah.
Yes, definitely. In your current position, do you teach and do research?
Yeah, I teach quantitative genetics and genomics, which is a new course here. And I teach, my undergraduate teaching, I think, is still kind of in flux. I inherited a course that has very, very low enrollment, and so I have to come up with something else. So I'm still figuring that out.
So I've seen this with my colleagues who are tenured professors and are trying to juggle the whole research, teaching, students, office hours thing. How's your time split between that? What are the expectations for how much time you spend on research and teaching?
The teaching, well, the expectation is, well, I have 40% teaching, and that here the policy is that that's 6 credits a year.
Okay.
Time-wise, I mean, this is gonna sound really bad, but basically I do my research during the day and I do my teaching I just prep for teaching at night. Like that's it's just between the hours of like 9 p.m. and 1 a.m. is when I do the teaching, and during the day I do the research. So
Okay. Yeah, that
I don't
sounds.
advocate that system, but I'm hoping it'll get easier because the teaching, it's just this when the first time is like developing all the material. So
Yes, the starting a new course is the worst.
yeah, so I'm hoping it's going to be less in the future. But I guess the thing is just as long as it's something you enjoy, then it's not, it's like a hobby after work. It's like
Yeah, I spent several years teaching in public school at this public school system, and yeah, that was not a hobby I enjoyed after work, but I did it. So yeah, but I think if I could have been teaching more of what I really wanted to teach, that would have definitely made a difference. So
oh yeah,
I'm hoping to in the next spring start teaching a course in plant sciences for non-science majors. So it's kind of more of a fun course, but all of our majors are required to take one, and so just to get them kind of a taste of science, and I'm looking forward to that. But yeah, I'm not looking forward to the whole creating a new course again.
Yeah, and I think it takes a while to figure out what you're going to enjoy. Like, so the class that I inherited was supposed to be kind of one of those fun classes that's like people take, like it's not required. I think what it effectively turned out as, it was like a class that if somebody needed a couple of credits, they would take it. Not they weren't interested in it. It was just sort of filler in their schedule. And then there was a lot of students that they didn't try, so they just failed. And I mean, it was just sort of it was something like, I know some people it doesn't affect them maybe, but for me that was just so like demotivating to see that. And like I just felt like I can't do a class like this. Like it's too painful for me. Like I can't spend all that effort in doing it and then have it be like something that I feel like is not going to be useful for the students. And it's like, what are we doing? Like, why are we doing it? Like,
Nobody wants to be here right now.
Why are we here? What are we accomplishing with this? I don't, it just feels really like a waste of time. And like, I don't know. I think different people see it differently, and some people probably would really enjoy that sort of class and teaching it and getting those rare students that would find it interesting. But that's something I learned about myself. I have to be teaching, like the one I'm teaching now, the students are learning something I think is extremely important for them to learn. I'm teaching them also like the skills, like how to actually analyze data. And that really motivates me. And it's a subject I just enjoy. So it's really like, doesn't feel at all painful. Yeah.
It makes a big difference.
Oh, huge difference. So I have to I have to do something like that for my undergraduate teaching. Otherwise, I think it's just too depressing.
So what undergraduate course did you inherit?
So it was a course about evolution,
Okay.
And it's not like it's uninteresting. I think it's an interesting course. It's just the students, they weren't in it for the right reasons.
Right. Yeah. Yeah, that's the thing about our non-science majors courses is everybody has to take one. And if you make one that isn't that interesting to a large number of students, you get students who just had to fill a spot and they just want the credit. That's it. And so they're going to do the minimum amount of work to get it. And then that isn't fun to teach for anybody. I can't imagine. So I've talked a lot. I really appreciate your thoughts on everything. I'm sad that the email got messed up because we usually have a lot of graduate students here, but that's unfortunate. I know that Dr. Murray is going to be back at 1:30. I made you host of the meeting, so unless you need anything else from me, I'm going to go.
Okay, that sounds good. So yeah, that'll give me a second. I have a bunch of messages I have to respond to. So this is the timing. So I'll just mute myself and stop the video for 15 minutes, and I'll just stay on.
Okay. And I just realized that I never stopped recording, which I can fix in the video later, but you'll have to actually hit the stop recording button because I made you host. Unless I can take it back. No, I can't.